Hi there. This is our dashboard demo. So we're going to start with our EDA section on our dashboard, which just goes over a bit of the data sets that we used and how we thought about them. So we had two main data sources, Open Meteor and NASA Power. Open Meteor is a hourly historical weather data source. Um, they provided us with things like temperature, wind data, and precipitation. And NASA power is more of these sort of like atmospheric radiation and sort of humidity, wetness type data sets relating to like overall environmental conditions, and that was a daily data set, so it's one data point per day. So if we look, yeah, you could see here what these data sets looked like in their original form. We had these four columns for open medio, temperature, wind speed, wind gusts, and precipitation. And then for NASA power, we had these columns, which cover things relating to, as I mentioned, soil like moisture, things to do with like radiation. Uh,
Yeah, it's
we
like
go, yeah.
a few of these like clear sky, all sky. These are different measures of solar radiation, aerosol in the air, soil humidity, and also like thermal radiation.
Yeah. And then part of our pipeline was cleaning the NASA data because it came with some like minus 999 null values when like they're missing a measurement. So we had 98 um such values. And then we just turn them into like proper nulls, basically.
And one other thing to mention about these is most of these were actually in like the 2025 to 2026 range. So that's why you'll see like the data set, a lot of it actually goes up to like sometime in like 2025 because a lot of the null NASA data was from 2026.
Yeah. So here's like our data processing flow visualized, I suppose, or broken up. We first pulled from our sources, cleaned NASA, as I mentioned, with those minus 999 null values. Then we joined by day. The NASA days were basically attached to each hour that of their relevant day. And then we basically built some other aggregates that we used in training, which I think we'll talk about later. But it's basically things like sliding window averages and like shifted from previous days. So we'll have a feature be the previous day's high temperature, previous day's precipitation, and things like
Yeah.
that.
It
Yeah.
would basically we'd have like three different lags, which we'll show you in a minute.
And then here you could see the size of our different steps of our data collection pipeline. So we had two final data sets, which was an hourly data set and a daily data set. To get our hourly data set, we basically used the open media hourly, and then we joined it on our NASA after cleaning, and we got this like after drop nulls table as our our hourly data set. But before we dropped those null values, it was slightly larger. There were not so many null values. So um, and here's a list of our columns. As I mentioned, we have temperature, wind speed, wind gust, precipitation, all from Open Meteor, and then there's some, or yeah, and then also some NASA data sets. All sky and clear sky are these radiation measures. And then we have a clearness index, which has to do with like particulate matter in the atmosphere. And then we have like other sky surface long wave. These are just different forms of radiation that can affect temperature. And then yeah, so the hourly and daily data sets are as they sound, hourly and daily. The daily is what we use to train most of the models, and we use the hourly in our final model. We'll talk about it when we go to the models. Um, yeah, and then here's like some examples of what our final data set looks like and what the columns look like. Um, so you can see here just all the columns that we described. And then here you can see same columns, but only at one per day granularity. But we also have these lag columns. So that's the lag one, two, and three are max temperatures from the previous days, uh, 1 day before, 2 and 3 days before. And then we have these rolling averages of the past 3 and 7 day highs, and then precipitation lag. Uh, and we're trying to predict this tomorrow max temperature column. So the way we split it up for the models is basically we used data from before 2024, and then 2024 on was our training set. So before 2024 was our test set, after was our training or our sorry, before 2024 was our training set, after was our test set. Um, Here are some, visualizations of different data that we were either using or targeting. So you can use this box to see the different NASA features, and then that graph above it is the max temperature distribution. This is the yeah, that target distribution is the distribution of the target values in our data set, and then yeah, and then we also have our daily temperature trend there. Anyway, so we also have these engineered features. So these were things like these sliding windows and the lags and things like that I mentioned. And then we have a feature correlation heat map here. So you can see that some of the features are highly correlated. So we did have like a multicollinearity that we handled in our training. We'll talk about it later. And yeah, these are some high correlation pairs, month and day of year, obviously, etc. Um,
Cool. Now we're gonna hop in to our modeling. And we have a little bit kind of like a story of our thought process of why we went kind of different directions. So our first kind of attempts were doing a k-means plus plus baseline and a linear regression baseline. Um, and we were kind of trying, hey, maybe unsupervised works, maybe supervised the best. We were kind of wondering maybe we can classify days by temperature because over the years you do have a bunch of days that are all relatively the same temperature. But this didn't work great. The errors were not good compared to the other models. Also, we weren't really getting a solid elbow in our chart of when it really was decreasing. So our number of clusters was a little iffy. So this really just wasn't working that great. Um, so then we switched kind of to a linear regression model, and we started just kind of integrating using our daily data set, integrating that, trying to predict the high temp of the next day. But then our coefficients blew up. So we were getting super, super high coefficients due to the likely the multicollinearity of our features. It was struggling of like how to balance kind of features that were representing similar information. So then we switched. To ridge regression. We did hyperparameter optimization using a grid search. That ended to be about 10 for the L2 penalty coefficient on that. And then you can kind of see here how ridge regression ended. Pretty nice stable coefficients. Um, and you can see it prioritized the current day's max temp the most to predict the next day's max temperature. And then you can see in this table kind of how that ended up. So ridge regression did better than that k-means baseline. And then from that, we then were like, how can we deal with this multicollinearity? How can we deal with, wanting to represent these nonlinear features, but still keep things explainable? So then we decided to try a decision tree. So we tried at first just a normal random forest regression model. Um, And then we also did hyperparameter optimization, random search on kind of like the number of trees in the ensemble model, the max depth, the feature count on the leaves, things like that. Um, and then we ran that, and we also got the important features here. And you can see both ridge regression and random forest both prioritize the current day's maximum temperature to predict tomorrow, as well as like the rolling average. They both had that pretty high up. Um, so then we had this, we were using this kind of daily data, the weather yesterday to predict the weather tomorrow. Then we were like, hey, why not, use the entire past week and use that hourly data set that we created um, to predict tomorrow's max temperature. So then that's when we decided to use a transformer because the transformers are with self-attention are good at kind of prioritizing, hey, when in the previous data um, has the most impact on tomorrow's data. And that's good because within a single day of data, we have this night to day cycle. So using attention to prioritize which hours are actually important to predict tomorrow's best temperature. That's very valuable was kind of our thought process there. So that using self-attention for that. So we trained our transformer model. You can see the loss was really nice. We did also random search for hyperparameter optimization on this, and you can watch in our presentation. We go through that in more depth, but really nice loss in the learning. You can see the actual values actually followed pretty well. So this is the train set 2024 to 2025 through 2025. We tried adding ReLU before our transformer encoder layer, but that actually ended up hurting us, so we took that out. But we basically start with an embedding with add positional embeddings, go through a transformer, and then predict the next day's max temperature. Worked pretty well. You can see up here the transformer had the best mean absolute error and root mean square error, but everything was like relatively similar. And you can kind of read here kind of about our tuning summary of what parameters got selected for each one using our grid search or random search. And then we decided to now pull in the Cauchy data. We basically pulled in which max temperature hit the market each day, and we simulated kind of our models picking on Cauchy. And surprisingly, actually, on Cauchy, the transformer model did the worst, which was kind of interesting to see. The ridge regression model, or sorry, the random forest did the best with 23%. So it hit its bet 23% of the time, which was kind of cool to see. Moving forward, this is just daily picks. We'd want to do this at an hourly level, but we're limited kind of on the data Cauchy gives us because they don't give hourly data long back. So we would want to actually pull data from them every day to record that for ourselves to then train. We'd also want to expand this to more cities to generalize it more. Right now, it's only New York City. So we also think expanding that out would be better. But yeah, so that's our project. We did trained four different models, tuned each of them, tested them on Cauchy. And yeah, thanks for looking at our demo. Hopefully you get a chance to check it out.